Hello everyone, today in this video we are going to talk about mutual induction, and after this video you should be able to define mutual induction and derive and apply the formula of mutual induction. So according to Faraday's law, when we change the magnetic flux through a coil, then there will be an induced in the coil, and the process of producing this induced EMF is called electromagnetic induction. And in this picture you can see, by moving a magnet near to a coil, we can change the magnetic flux through the coil, and the galvanometer shows the deflection due to the production of induced current. So there are two types of induction. One is self induction and another is mutual induction. So self induction we have done in our previous video. The link is given in the description box if you want to go through it. And in this video we'll talk about mutual induction. So suppose I have two coils. In one coil there is a switch and another coil is connected to a galvanometer. So at 0 seconds, suppose the coil number 1 is switched off. So at 1 second and 2 seconds there is no current in coil number 1. At 2 seconds, suppose I press the switch, and when I press the switch the magnetic field is produced, and you can see the magnetic flux through the second coil changes. So as we already know, when the flux changes there will be induced EMF. So during 2 seconds to 3 seconds there is change in flux, so the galvanometer shows the deflection. And in 4th, 5th and 6th second I am keeping the circuit on. So that means during 3, 4, 5 and 6 there is no change in flux. So suppose at 6th second I switch off the circuit again. Now you can see, while going from 6 seconds to 7 seconds there is change in flux, some flux to zero flux. So that time also there will be change in flux and there will be induced EMF, and the galvanometer shows the deflection in opposite direction as compared to previous one. And 7, 8 and 9 second I am leaving the circuit off. So you can see between 2 seconds and 3 seconds there is change in flux, and between 6 seconds and 7 seconds there is change in flux. So within that time only there is change in flux and deflection in galvanometer. Other time the galvanometer do not show any deflection. So if you plot the graph, so between 2 seconds to 3 seconds there is induced EMF in one direction, and between 6 to 7 there is current in another direction. So other time we don't have any induced current. So this is the same experiment. Now when I switch on this, there will be magnetic field and the flux will change. There will be a momentary deflection in this galvanometer. So you can have your eye on this galvanometer when I switch on. So you saw that the deflection is for a moment only. Now similarly when I switch off, the flux will change and there will be induced EMF in opposite direction. So this is how we change the magnetic flux by changing the current in one coil, and this process is called mutual induction. The process of producing EMF in one coil by changing the current in another coil, and the direction of the induced current is given by Lenge's law. Now in this video we will see the mutual induction between two coils. So in this picture we have two coils. So in this coil a bulb is connected and there is no cell, so that means the bulb should not glow. So in this coil we are giving AC current. So AC current changes its direction frequently, so that it produces the magnetic field which changes the direction frequently. So when I bring this coil near to this coil, that time the flux through this coil changes because of the changing magnetic field, so due to which an EMF is produced in this coil and which helps in glowing this bulb. So you can see now we are bringing the coil near and now the bulb is glowing. So this is mutual inductance between two coils. So now this is the same experiment I have explained before. So on switching on this coil, the direction of induced EMF is in one direction, and while switching off, the direction of induced EMF is in another direction. So only while switching on and switching off there will be change in magnetic flux and induced EMF. Other time we don't have induced EMF. So we are considering two coils, coil number 1 and coil number 2. So when we change the current through coil number 2, the flux through coil number 1 changes. So that means I can write the flux in coil number 1 depends on current in coil number 2. So when I change this proportionality sign, that time I can write flux is equal to a constant into current, and this M is called coefficient of mutual inductance between two coils. And if you want to find the EMF, then we can use Faraday's law. EMF is equal to the rate of change of magnetic flux with negative sign. So if I put the value of flux out here, Mi, then I will get EMF is equal to minus M di upon dt. So now let's define the coefficient of mutual inductance. So we know the formula, EMF is equal to minus M di upon dt. So if you put di upon dt is equal to 1 ampere per second. So di upon dt means change in current per unit time. So that is, the change in current is 1 ampere per second. So that time I can write EMF is equal to M. That means the mutual inductance between two coil is equal to the EMF produced in coil number 1 when the rate of change of current in coil number 2 is 1 ampere per second. So now we'll find the unit of mutual inductance. So this is the formula for EMF, and if I take M this side, then so unit of M will be unit of EMF, that is volt, into unit of time, that is second, divided by unit of current, that is ampere. So unit of is volt second per ampere, and another name for volt second per ampere is Henry. So SI unit of mutual inductance is Henry, and another units are volt second per ampere and Weber per ampere. Weber per ampere because mutual inductance is equal to flux by current. So flux is Weber and current is ampere. So now let's find the dimension of mutual inductance. So this is the formula, flux is equal to Mi, M is equal to flux by I. So we know flux is equal to magnetic field into area. So I can write M is equal to Ba by I. So for I have to replace this B. So in order to replace this B, I'll make use of the formula, force is equal to magnetic field into charge into velocity, and B is equal to F by QV. Now M is equal to F into A by QVI. So now we'll put the dimension of all the variables of this side. So for force it is M1 L1 T minus 2, area is L square, charge is AT, and velocity is L T minus 1, and current is A. So if you solve this, you will get M1 L2 T minus 2 A minus 2. So now we'll derive the formula for mutual inductance between two solenoids. So we are considering two solenoid. One solenoid is large and one is the smaller solenoid which is inside the large solenoid, and they are coaxial, meaning their axis is same, and the radius of small solenoid is R1 and the radius of larger solenoid is R2. Number of turns in small solenoid is N1 and number of turns in solenoid number 2 is N2, and the length is same for both the solenoid. So this diagram is little complicated, so we'll draw a simple one. So you can see L is the length, R1 R2 radius, N2 N1 number of turns. So small n2 is the number of turns per unit length of outer solenoid, and n1 is the number of turns per unit length of inner solenoid. Now we are sending the current through the outer solenoid and we are producing the magnetic field inside the small solenoid. That means when we send the current through larger solenoid, the flux through inner solenoid will change. So magnetic field due to current I2 in S2 is given by B2 is equal to mu naught N2 I2. So I am using N2 I2 because the magnetic field is produced by solenoid number 2, which is the larger solenoid. So due to this magnetic field due to the larger solenoid, there will be flux through the smaller solenoid. So the flux through the coil number 1 or solenoid number 1 is given by magnetic field due to coil number 2 into area of coil number 1 and number of turns in coil number 1. So now I'll put the values. So B2 is mu naught N2 I2 and area of small solenoid is pi R1 square, and for N1 I can write small n1 L1. Small n1 is number of turns per unit length of solenoid number 1, and if you open the bracket you will get this. So flux 1 is given by this. Now if we change the current through solenoid number 2, the flux through solenoid number 1 will change, and the relationship between flux and the current is given by phi 1 is equal to M12 I2. So this is the first expression we have discussed. So M12 is the mutual inductance of coil 1 with respect to coil 2. So now if you take M this side, then it will be flux by current. Now I'll put the values. So the flux 1 is this and current is I2. So we can cancel this I2 and this I2. So M12 will be given by mu naught N1 N2 pi R1 square L. Now this is the mutual inductance of coil number 1 with respect to coil number 2. And if you want to find the mutual inductance of coil number 2 with respect to 1, that time we have to reverse the case. That means we have to send the current through solenoid number 1 and change the flux through coil number 2. That time mutual inductance of coil number 2 with respect to 1 is given by this expression. So we just need to change the subscript from 1 to 2. So out here you can see M1 M2, here I'm changing to 2 into 1. So the remaining formula remains almost same, only we have to change for R. So now you can see M12 and M21. So now if R1 and R2 is equal, that means the solenoids are of equal radius. That time M1 and M12 and M21 will be equal, because as you have seen there is only change in R1 and R2. So if you are using the coil of same radius, that time mutual inductance of coil number 1 with respect to 2 and mutual inductance of coil number 2 with respect to 1 will be equal. Now if you put small n is equal to capital N by L, for N1 you will write capital N1 by L, and for N2 you will write capital N2 by L. That time the mutual inductance will be given by this. So for M12 and for M21 I am writing M only because they are equal. And now if you want to find the induced EMF, that is EMF is equal to minus M di dt. That time the value of M will be this di upon dt. So this is the final expression for mutual inductance between two coils, and this area is the common area between two coils. So there are several factors in which the mutual inductance depends. So it depends on number of turns in each solenoids, and it depends on the common area between the solenoids, and it depends on what kind of material we are keeping inside the solenoids, and it depends on the separation between two coils, and it depends upon the orientation, in which position we are keeping the solenoids, and it depends on length of the solenoids also. So in this question 0.5 volt of induced EMF is developed in one coil when the current in second coil is changed from 5 ampere to 2 ampere in 300 milliseconds. So we have to find the mutual inductance, and the time is 300 milliseconds. that means milli means 10 to the power minus 3, so we have 2 zeros, so it will be 3 into 10 to the power minus 1 second. Now you can put the values and find the mutual inductance. So this is the second question: what is the mutual inductance of a pair of coils if a current change of 6 ampere in one coil causes the flux in second coil of 200 turns to change by 12 into 10 to the power minus 14 Weber per turn. So now flux per turn is given, so that is 12 into 10 to the power minus 4. So total flux will be flux per turn into number of turns, so that will be 2000 into 12 into 10 to the power minus 14. So now you can use this formula, M is equal to flux by current. So current is already given 6 ampere and flux is 2000 into 12 into 10 to the power minus 14. So you can find the coefficient of mutual inductance. So now one more question: over a solenoid of 50 centimeter length and 2 centimeter radius having 500 turns is wound another wire of 50 turns near the center. Over a solenoid of 50 centimeter length and 2 centimeter radius having 50 turns is wound another wire of 50 turns near the center. Calculate the mutual inductance of two coils if the current in primary changes from 0 to 5 ampere in 0.02 seconds. What is the EMF induced in secondary coil? So length of the solenoid is given, that is 50 centimeter. I will convert it into meter, and radius is also given 2 centimeter, so 2 into 10 to the power minus 2 meter. So N1 and N2 is given. So number of turn in first solenoid is 500 and number of turns in second solenoid is 50. So now change in current is 5 ampere to 0 ampere and time is 0.02 seconds and area is pi r square. Now mutual inductance between two coils is given by mu naught N1 N2 A by L. So area we already have, number of turns are also given and length is also given, so you can easily calculate M. So from there you can find the induced EMF using this formula. So let's summarize the video. So the mutual inductance means the production of induced EMF by changing the current in another coil, and the formula is given by flux is equal to Mi and induced EMF is minus d phi dt. So if you put the value you will get minus M di upon dt, and the unit of coefficient of mutual inductance is Henry, and the formula of mutual inductance between two coils is given by M is equal to mu naught N1 N2 A by L, and the mutual inductance between two coils depends on several factors. So I think this is the end of the video. Don't forget to like the video and subscribe the channel. Thank you. So why